Hello everyone, welcome to Maths Wheels. In this session, we are going to cover Theorem 6.7 and Theorem 6.8 of Triangles chapter. Let's start with Theorem 6.7. It states that if a perpendicular is drawn from the vertex of the right angle of a right triangle to the hypotenuse, then triangles on both sides of the perpendicular are similar to the whole triangle and to each other. What does this mean? Let's say we have a right angled triangle ABC as shown in the figure. So angle B is 90 degree. Now the theorem states that if a perpendicular is drawn from the vertex of the right angle. So in the figure, which is the vertex of the right angle? B. So from the vertex B, we have to draw a perpendicular to the hypotenuse. So let's draw the perpendicular here. Let's take this point as M. So this is given. Now what we have to prove? Read the rest part of the statement. That is, triangles on both sides of the perpendicular are similar to the whole triangle and to each other. Now if you see the figure, there are two triangles on both the sides of perpendicular PM. This is the first triangle and this is the second triangle. So we need to prove these two triangles, triangle AMB and triangle CMB, are similar to the whole triangle, that is triangle ABC. So if you read the statement properly, it is written that similar to whole triangle and to each other. That means we have to prove this first triangle AMB similar to the whole triangle ABC. Also, we need to prove this second triangle CMB similar to whole triangle ABC. And also we need to prove these two triangles AMP and triangle CMB are similar. Let's write down what is given. A triangle ABC, which is a right angle triangle. So angle B is equals to 90 degree. And BM is perpendicular to AC. This is given. And what is to prove? First write the two triangles similar to whole triangle ABC. So first triangle is triangle EMB similar to whole triangle ABC. Second triangle is CMB similar to whole triangle ABC. And third is both triangle 1 and 2 are similar to each other. Triangle AMB similar to triangle CMB. This we have to prove. Let's start the proof from here. Let's first prove the first condition, that is triangle AMB similar to triangle ABC. So let's write in triangle AMB and triangle ABC. If you see the figure, angle A is common in both the triangles. That means this angle. Write this, angle A is equals to angle A. Reason is since common angles. Now see the second angle. In triangle AMB, angle AMB is 90 degree, right? This angle. And in triangle ABC, angle ABC, that means this angle is 90 degree. Reason, since each is 90 degree. So in both the triangles, these two angles are equal. So we can apply angle similarity criteria. Therefore, by angle criteria, we can write triangle AMB is similar to triangle ABC. Here we have proved the first part. Now let's prove the second part. Now if you see, second part is triangle CMB. In second part, we have to prove triangle CMB similar to triangle ABC. We can prove this similar to the first part we have done. We can write similarly triangle CMB is similar to triangle ABC. How this will be similar? Angle C equals to angle C in both the triangles, because angle C is the common angle, and angle CMB is 90 degree. Also in triangle CMB, angle CMB is 90 degree. Also in triangle ABC, angle ABC is 90 degree. So by angle criteria, these two triangles will be similar. Now let's see the third part. We have to prove triangle AMB is similar to triangle CMB. So write in triangle AMB and triangle CMB. Now just think how we can prove triangle AMB similar to triangle CMB. Just think, can we take help of first two parts we just proved? Yes, if you see the first two parts here, triangle AMB is similar to triangle ABC, and with the same triangle ABC, triangle CMB is similar. So if we take this equation as 1 and this equation as 2, we can write from 1 and 2. That means we have first triangle similar to second triangle and second triangle similar to third triangle. So first and third triangle will be similar, right? So therefore we can write from 1 and 2, triangle AMB is similar to triangle CMB. And this is the third part which we had to prove. We can write hence proved. Now next is Theorem 6.8, which is referred to as Pythagoras Theorem. As you know, we are already familiar with this Pythagoras Theorem from our earlier classes. We had made use of this theorem in solving certain problems. We have also seen a proof of this theorem in class 9th. Now, we shall prove this theorem using the concept of similarity of triangles. And in proving this, we'll make use of Theorem 6.7, which we learned previously. Let's start with the statement. The theorem states that in a right triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides. So let's say we have a triangle ABC, which is a right angle triangle. So angle B is 90 degree here, as shown in the figure. So which is the side opposite to right angle? AC. So AC is the hypotenuse here. And what are other two sides? AB and BC. So what we need to prove? Square of the hypotenuse, that is AC square, is equals to sum of squares of other two sides. That means AB square plus BC square. So let's write what is given and what we need to prove. Given a right triangle ABC in which angle P is equals to 90 degree. This is given. Let's write to prove. Square of hypotenuse, that is AC square, is equals to sum of square of other two sides. So AB square plus BC square. Now to prove this theorem, we need a construction. So let's write the construction. In the figure, we will do the same construction as we did in Theorem 6.7. That means similar to previous theorem. So from the vertex at the right angle, we'll draw perpendicular to the opposite side, that is hypotenuse AC. Let's take this point as point D. Write the same here in the construction. Draw BD perpendicular to AC. Now let's start the proof. To prove this theorem, we'll make use of Theorem 6.7. What is that theorem? If a perpendicular is drawn from the vertex of the right angle of a right triangle to the hypotenuse, then triangles on both sides of the perpendicular are similar to the whole triangle and similar to each other. So if we use this theorem in our triangle ABC, where we have drawn BD perpendicular to hypotenuse AC, we can see the first triangle ADB, which is on one side of this perpendicular BD, and the second triangle BDC, which is on other side of the perpendicular BD. So using theorem 6.7, we can say triangle ADB is similar to whole triangle ABC, and also second triangle BDC is similar to whole triangle ABC, and also these first and second triangles are similar to each other. That means triangle ADB is similar to triangle BDC. Let's first write the first triangle ADB and whole triangle ABC. In triangle ADB and triangle ABC. Using theorem 6.7, triangle ADB will be similar to triangle ABC. And you can write this is by using theorem 6.7. In the exam, you need to write the complete statement of 6.7. What is it? If a perpendicular is drawn from the vertex of the right angle of a right triangle to the hypotenuse, then the triangles on both sides of the perpendicular are similar to the whole triangle and to each other. Now, since these two triangles are similar, the ratio of the corresponding sides will be equal, right? Now, if you see the to prove part, we need AB square. And in both the triangles ADB and ABC, AB is the common side. So we'll try to get AB square from these two triangles ADB and ABC. So let's first write the ratio of the sides. Now in triangle ADB, A is at first position and B is at third position. So from the second triangle ABC also, we'll take first and third position. That will be AC. So what will be the ratio? AP by AC is equals to, now what we need is a AB square. So if we get AB in the denominator here, and if we cross multiply these two terms, we can get AB square, right? So this AB is from the second triangle, which is first and second position. So in the denominator, we'll write from the first triangle. So AD will be the numerator. And this is what? This we got by CPST. That is corresponding parts of similar triangles. Now just to the cross multiplication, what we get? AB square is equals to AD into AC. Let's take this as equation 1. Similarly, let's find BC square. To get BC square, we will consider triangle BDC and triangle ABC, because BC is the common side in both the triangles. So we can write in triangle BDC and triangle ABC, using theorem 6.7, triangle BDC will be similar to triangle ABC. This is by theorem 6.7. In the exam, you need to write the complete statement of 6.7. I'm just writing here the theorem 6.7. Now since triangle BDC is similar to triangle ABC, we can write the ratio of corresponding sides. What we need? BC square. So we'll write the ratio of sides containing BC. Now if you see the first triangle BDC, to get BC, B is at first position and C is at third position. So let's write here BC upon. In the second triangle ABC, we'll have to take first and third position, that will be AC, equals to sign. Now take BC from the second triangle ABC here. So this is BC. B is at second position and C is at third. So let's take the same from the first triangle also. It will be DC, right? And now if you cross multiply this, what you get? BC square equals to DC into AC. Take this as second equation. Now what we need is AB square plus BC square. So we need to add first and second equations. So adding 1 and 2 will get AB square plus BC square. This will be the left hand side. Right hand side will be AD into AC plus DC into AC. Now if you compare this with the to prove part, we have got the right hand side, but we are yet to get the left hand side AC square. So let's try to get AC square from this. AC is common here. So let's take AC common. What is left? AD plus DC. And let's write left hand side same, AB square plus BC square. Now if you see in the figure, AD plus DC is equals to AC, right? So in place of AD plus DC we can write AC, and this will get multiplied with AC, it will be AC square. So this will be equals to AC square. Therefore you can write AB square plus BC square is equals to AC square. And this is what we have to prove. You can write hence proved.